now that we are live. 2.1 is all over increasing, decreasing, and piecewise functions. That's what that third word is. And increasing, decreasing, and piecewise functions are very important. So we are going to deal with those today. Chapter 2 is all over functions. So we are going to be doing a lot of graphing. We're going to be doing a lot with our functions during this chapter. But first, let's talk about increasing, decreasing, and constant. I have given some very generic graphs in these first three little sections up here, and then given some information. The information makes it a little bit more mappy and a little bit more complicated than I think it actually is, but I still provide it because it does make sense once I explain it a little bit further. For this first graph, it says when A is less than B, so notice where A and B are, they're right here on the x-axis. So when A is less than B on a given interval, that's what I means. In any given interval, if we're looking at a graph and A is less than B, then f of A less than f of B also means that f is increasing on that interval. So remember, the f of A and the f of B are your y's. So what it's saying is if you're looking on a given interval and the x value, like A is less than B, and the y value, A is less than B, for those points, then you're increasing. In layman's terms, if you look at a graph and you read it from left to right and it moves upward, then it's increasing. That's what all of that math says. If you read a graph from left to right and it's going up or it's increasing, then it's increasing. So don't let all the math confuse you, like all the gurgledy written math speak make it more complicated than what it actually is. If this x is smaller than this y, or this x, then that y had better be smaller than that y, or it's not increasing. That's what it says. And it does say on a given interval. We're not talking about the entire function, because oftentimes a whole function is not going to be just one of these things. You're going to have sections of the function that are increasing, decreasing, or constant, not the entire function as a whole. And so that's why we have to use that special indicator that says on an interval or in a given interval. So if we look at the middle graph up here at the top, it says if A is less than B on our x-axis, but if the y value is greater for f of A than it is for B, then you are decreasing. If you look at a graph and read it from left to right and it's going down, then it's decreasing on that interval. And constant means that for all of the A's and B's that are in a given interval, the y's stay the same. They are constant. That's where you have a flat line. So those are the three different types of intervals you're going to be looking for. And you're going to be asked to identify where on a given graph you are increasing, where you are decreasing, where you are constant. And sometimes your graph will only decrease. If you're talking about a linear function, it's only going to increase, decrease, or be constant, or I guess you could say neither if it's an undefined, but then it's not a function. So if you are a function, you can be all three of these at different intervals. So this picture that I've drawn here for our first example says determine on what intervals the function is, and then it says ... So let's figure out the interval for which it is increasing. And if it says interval, that means it wants it in interval notation. That's where we use our parentheses or our brackets, and we put the low value and the upper value. So I need to figure out where this graph is increasing. So I'm going to read it from left to right. I'm going down, so I'm not increasing. Then I'm sliding straight across, so I'm not increasing. But then after this point, I start increasing. So what is the first value in terms of x's that I start increasing at? 3. Okay? Because right here when x is 3, that's when my graph starts suddenly climbing. Now, we're always going to use parentheses. Right? I'm saying that, yes. Just making sure I'm not making stuff up. The reason why we are going to use a parenthesis here is because up until 3, what happens? We're constant. So at that one point, it's kind of like a turning point. At this point, what's happening is we're growing from constant to increasing. And so we're not going to include 3 because really it's doing 2 different things. And then it's going to increase until x is what? 5. Because once we hit 5, it starts decreasing again. And then we've covered our whole graph. There's nothing else to do. That is the only interval on which we are increasing. So we increase from 3 to 5. Next, let's look at decrease. Sorry, that says decrease. So what is the first interval that we are decreasing on? Oh. Negative infinity to where? Yeah, because if we start at the very far left side of our graph, we are immediately decreasing. And that arrow at the end of our graph means that that's going up and to the left forever, which means we are forever decreasing as far out as we can move to the left. So it actually is negative infinity. And then we keep going until we hit that point, which is where it turns into a constant, and that's when x is negative 1. Is there any other interval on this graph where we are decreasing? Yes. So we are constant, then we are increasing, and then as soon as we hit 5, we start decreasing again, and it goes on for forever until we hit infinity. So 5 to infinity. Notice that all of these intervals, when we are doing increasing, decreasing, and constant, are going to be given with the x values. So where are we constant on this graph? Yeah, right here from negative 1 to 3. And notice if we actually listed all of these in order, negative infinity to negative 1, negative 1 to 3, 3 to 5, and 5 to infinity, we cover the entire span of this function. Are there any questions? Let me move that over. On how we find the increasing, decreasing, or constant sections of a given graph?
Do the y's not play a part?
They will in just a minute. Okay. They don't on the intervals of what the function is, but we are going to be asked about relative minimums and maximums, and that's where the y's come in, because that tells us how high up something goes or how far down something goes. And actually, I can just slide that right on up for you. So relative minimum and maximum, aka the turning points. I even mentioned up here that we aren't including those points, these turning points, when it goes from decreasing to increasing or decreasing to constant, because kind of 2 different things are happening at that. But it's at those turning points that we get either a relative minimum or a relative maximum. Maximum or maxima happen at the peaks, at the tippy tops, when you go from increasing to decreasing. When you go from decreasing to increasing, that's where you're going to get your relative minimums. And I say relative minimums or minima because notice that of the 3 minima, whatever it is, one of them is obviously far lower than the other 2. So this one would actually be the ultimate max or minimum down here. But we're saying relative because if I look at just one section of a graph, then that C1 is the relative min. Where your turning points happen, where these maximums and minimums happen, they happen at the x values. But their value is their y values. So this is where the y's will finally start coming into play. So the relative max at C2, right here, has a value of f of C2, or whatever the y is there. So it happens at the x, but you're given a value of whatever the y is. I give another example with the minimum where I say the relative minimum at C1, that's your x value, and it has a value at f of C1, whatever that is in terms of the y's. So the turning points, or these minimum and maximums, happen when you shift from decreasing to increasing, or increasing to decreasing. Are you ready for me to flip it on over? See some problems or examples? Okay. So we're going to start graphing stuff. Here's a little make your life easier moment. This is asking you to graph f of x equals x squared minus 4. You're going to give the intervals where it's increasing, decreasing, and constant, and you're going to find any and all relative maximum minimum. Now, if you haven't graphed a function in a long time, you might not recognize what this function is supposed to look like. There is a group of functions that are known as your basic functions, your mother functions. I like that terminology better. I think it's funny. That we will discuss a lot more in Chapter 2, Section 5, when we talk about transformations of functions. And there's a nice table in your textbook for 2.5 of these basic functions. But I'm going to show you, I also drew out pretty much the table in the notes for 2.5. These basic mother functions are on page 129 of your textbook. And I strongly, strongly, strongly recommend memorizing these. Notice these are very generic graphs. There's no little tick marks to show you the value at 1, 2, 3, and 4. But what it does is it gives you a general overview of what this function is doing. And so if I see something that looks like y equals x, I know that's going to give me a linear function. It's going to give me a line. And I know what that looks like in my head. If I see something that has an x squared, I know that's a quadratic function, and it's going to give me a u that either opens up or opens down. But then I know a general idea of what it looks like. Absolute values always look like a v. And so that helps me just to have a very basic picture in my head of what is going to happen with these graphs. And if you memorize this set of mother functions, your life as you move forward in this class and any other math class you have will be a lot easier, just because you don't have to go through the graphing by plotting points method that we're going to do today. So 2.5 notes, page 129 in your textbook. If you Google mother functions, they'll come up. So I pulled that over so that we can see, in general, if this says x squared minus 4, we know, okay, it's going to look a little bit like the quadratic function in some way, shape, or form. But we're going to pretend like we don't know anything about graphing, that we don't know how to do this. So what we do is we graph by plotting points. That's where I do my table, where I have my x value, and then I have my function column, and then I have my y or my f of x column. I strongly recommend that when it comes to graphing and you're using the point plotting method, you do 2 negatives, you do 0, and you do 2 positives, and that will give you a pretty good overview of what is happening in that graph, because you get to pick whatever values you want for x. So I would do -2, -1, 0, 1, and 2 to give me a good idea of what's going on in this graph. Again, if you memorize your mother functions, and especially after 2.5 when we learn about translations, graphing gets a lot quicker. But for now, we're going to take x is -2. We're going to plug that in to get out our y's. -1. And 1. And 2 squared minus 4 equals 4 minus 4 equals 0. Once you've filled out your table and gotten some idea of what's going to happen, you can start plotting those points that you get. I had -2, 0. I had -1, -3. 0, -4. 1, -3. And 2, 0. Here's why knowing what your mother functions look like is important. If I just graphed that, I could make it a really sharp V shape, and it would still line up with everything that I have. But that's for an absolute value. I need this to be a little bit of a rounder shape because this is a parabola with our quadratic. It's also important here with this one that you can kind of see why I tell you to pick 2 negatives, 0, and 2 positives. Think if I would have just chosen 0, 1, and 2, I would have only had this as my graph. And I would not have a full picture of what's going on, and I would have an inaccurate graph for this equation. So that's why I tell you pick 2 negatives, 0, 2 positives. That usually gives you a pretty good picture of what is going on. And there's my other picture in my notes. So graphing it was one part. But then we have to find our intervals where we're increasing, decreasing, and constant, and we need to find any and all relative maximums and minimums. So, where am I increasing? From where to where, using your x values? Using x. Yeah, we got to use our x's. So we start increasing right here. This is called your vertex of your parabola. We'll learn a lot more about parabolas later on in the class. But from 0 on to infinity, as we move on our x's, we're going to be increasing or moving up. We are decreasing from when to when? Negative infinity to 0. And where are we constant? Yeah, we're not. We're never constant. So I think these are multiple choice on your homework, where it'll say you're constant and then it gives you the opportunity to type in an interval, or it'll give you there are no intervals for this graph that are constant, and you click that one. This one has no constant intervals, so you'd have never. And then it needs to know if we have any relative minimums or maximums. What do you think? Yeah, we have to have at least one because we had an increasing interval and a decreasing interval, so we have to have some relative min or max. And in this case, since we go from decreasing to increasing, we have a relative min. Relative min. Hopefully looking at the graph, you can see it's like the lowest point in the graph on this section. And so it's a relative min that happens at the x value. So it happens at 0, and it has a value of -4. So it happens at the x, but it has a value of -4. And
why is it a relative minimum and not an absolute minimum?
In this case, for this graph, it is both. Yeah, it is both. But like on that other graph that we just had on the front, when we talked about minimums and maximums, if I had only been looking at this part of the graph, C3 is a relative min because it's not actually the lowest that it ever goes. And when we start talking about like on a graph like this that has a lot of relative mins and maxes, we can't talk about even an absolute maximum if we're thinking about the endpoints because it goes on for forever. And so we keep it as a relative min because we're just talking about that one section. But you are correct. In this graph, the relative min would be the absolute as well. Are there any questions on how we graphed this, how we came up with our intervals, or our minimums, or any of that kind of stuff?
When it's typing the answer, is it basically just how you have that written relative min at 0 has a value of -4?
It will tell you.
Okay.
Yeah, usually I think it says relative, like you have an option of like x equals, and then it'll tell you like you put in the 0.
Okay.
Or it'll ask you where it's happening and then what is the value. So it does make it pretty apparent which one you put where.
Okay.
Good question. All right, let's talk about some piecewise functions. That was the word nobody could read. Piecewise. I get why you couldn't read it. Piecewise. So piecewise functions are functions that use different output formulas for different pieces of the domain. What that means is you're not looking at one function over the entire span of your graph. You're going to look at one function for one section, and then you're going to look at a different function for a different section, and you're going to look at a different function for a third section, or so on and so forth. Don't cheat. I'm going to have to write these down, so hold on. Okay. There we go. So piecewise, you're using different pieces of different functions to make one big function is what's happening. And when you look at a piecewise function, like in this example, it will have a curly bracket like a systems of equations does, because that's really what you have. You have a bunch of different equations or a bunch of different functions, but then it's going to tell you over which given interval that we are considering that function. So for this first example, we have f of x equals x plus 1 when x is less than -2. So when x is less than -2, we have a linear function. That's what's happening. Then we have f of x equals 5. That's just a constant flat bar right up there at 5 when x is between -2 and +3. And then we have part of our parabola for that x squared for when x is greater than 3. So we've got lots of different stuff going on, and that's okay. And you will be graphing some of these. That's what's coming next. But this first problem, what they're asking us to do is find different function values. And so they're asking us to find f of 5 and f of -3 and f of 0 and so on and so forth. But in order to do that, we have to consider which function we are using. It's not that we just plug this in, because we're dealing with 3 different equations. So we have to know which equation to use at which time. So when f of 5, we need to figure out which function we're going to use for f of 5. Well, is 5 less than negative 2? No. Is 5 between negative 2 and 3? No. Is 5 greater than 3? Yep. So we're going to use that one. We're going to use x squared. So we're going to say 5 squared, so that gives me 25. We have to figure out which function we're using, then we plug it into that function and compute out the y for it. So it's still the same plug and chug style problems that you've encountered in previous math classes. It's just now you have to do a little bit more deduction before you can actually do your math. So f of negative 3, well, that's less than negative 2, so we're going to use x plus 1. F of 0, that lies between negative 2 and 3. So what is f of 0? 5, yeah. There's nothing to plug into because it is a constant function. What about f of 3? That's D. It's also 5 because if it lies between negative 2 and 3 where it's less than or equal to 3, so it's still going to be 5. We have to look at those inequality symbols. F of 4, that's greater than 3, so that'll be 4 squared, which is 16. And what is f of 10? Yeah, it's 100, because that'd be 10 squared, which is 100. Are there any questions on how we were able to deduce which of those functions we used in order to come up with our solutions? Not too bad, right? All right, let's graph them. There's not really any notes for graphing. We're just going to graph them. When you're graphing a piecewise, what you're doing is really you're graphing multiple graphs on the same Cartesian coordinate system. You're just graphing them on different sections of that graph. So it says graph g of x equals 1/3 x plus 3 for when x is less than 3. And we need to do negative x when x is greater than or equal to 3. So we're still going to approach this the same way we approached our parabola just a few minutes ago. We're going to do the point plotting system. We're going to make a table. We're just going to have 2 different tables because we're going to have one for the top function and we're going to have one for the bottom function. And they limit us a little bit more on what our x's should be. So I have my x. G of x, I'm looking at the top function, is 1/3 x plus 3. And then we have our y. Now I told you that you can use whatever x's and y's, or excuse me, whatever x's you want to. When it comes to piecewise, you have to limit it to what they tell you. So x has to be less than 3. So when I pick my x's to plug into this function, I need to pick x's that are less than 3. I'm also going to be a little bit smart here and think I don't want to be dealing with fractions very much, so I'm going to list multiples of 3. What I mean by that is, well, 1, I'm going to do 0, because 0 is less than 3, and if I multiply by 1/3, that's not too bad. So I'm going to do x is 0. But if I multiply 1/3 by, let's say, negative 3, then that gives me negative 1. Like, I'm just trying to simplify the algebra here. And then I'll do negative 6. Because all of those numbers are less than positive 3, and all of them algebraically are going to do nice algebra, quote unquote. So I have 1/3 times 0 plus 3. That'll give me 3. 1/3 times negative 3 plus 3 gives me negative 1 plus 3 is 2. And if fractions aren't your thing and you really struggle with fractions, let me tell you, they're not going to go away. I have a lecture video from Math 20 on 1.3 that is a really good reference tool for fractions. Negative 6 divided by 3 is negative 2. Okay, so 0 to 3, 1, 2, 3, oops, I was going to use green. Not that it really matters all that much. Negative 3 is up at 2, and at negative 6, which would have been one more tick mark, I'd be up at 1. I will say on your notes and homework, I think all of these are multiple choice. Now, all the way up until x is 3, I'm going to have this line. This is a linear function. Please give some grace on this not totally connecting right there. All the way up until x is 3. So at x is 3, because it's strictly less than, I'm going to use an open circle right here. Again, give grace right here. And a bigger dot. Now, that's not all of it. We're not done. That was just that top function. So now we're going to do the same process for g of x is negative x for when x is greater than or equal to 3. So since this one does have the equals to, I'm going to have 3 be the first x value that I'm going to plug in. And since I have to go then larger than that, I'm going to go 4 and 5. There's not really anything to compute here. Because when you plug those in, you're just changing the signs on them. And since it does equal for this range, I'm going to use a closed-in circle in that first point of 3, negative 3. 3, negative 3. And then 4, negative 4. 5, negative 5. Again, I have another linear function. And this is a piecewise function. It does the green equation until you hit 3, and then it's going to jump down, and it's going to do the red equation until you go on for infinity. Are there questions? Okay, they're so quiet today. All right, we've got one more. Okay? Can we muster through one more? Yeah, we can. This one's a little bit more interesting. This one's got 3 different things going on.
Is that just 4x squared, or is there a symbol in between two?
That's a minus.
Okay, that glares.
Yeah, sorry. 4 minus x squared on that one. Oh, I moved it. Sorry about that. Please ignore that squiggle. That's not anything. Okay. So this piecewise function has three different sections. It has f of x equals 4 when x is less than or equal to 0, 4 minus x squared when x lies between 0 and is less than or equal to 2, and then 2x minus 6 when x is greater than 2. So if you know your mother functions, this is where it comes in helpful, because if I have f of x equals 4, I know that is a horizontal line at 4, and that this is a parabola, so an upside down u, and that this is a line. It's a linear equation. So that kind of helps me to picture what's going to happen in these three different sections. So until x is greater than 0, all we have going on is y equals 4, or f of x equals 4. So I'm going to draw that in first. You don't have to make a table of any sort for that. 1, 2, 3, 4. And it goes all the way to 0, and we do include 0 in this one because it is at less than or equal to 0. So there's our top equation. Now we are going to have to use some tables to point plot for our next two sections. So we have x, we have f of x equals 4 minus x squared, and we have y. And we have to stay between 0 and 2 in this case. So since we're just staying in between those two numbers, I'm just going to do two numbers this time. I'm going to do 1 and I'm going to do 2. Because it says less than or equals to 2, so I can use that as a point in this form. So I have 4 minus x squared, which is 1 squared, which is 4 minus 1, which is 3. 4 minus 2 squared is 4 minus 4, which is 0. So I have 1, 3. And 2, 0. Notice I make it a little bit of a rounder look there. And that's because I know that it's going to be a parabola, and parabolas look like U's. We're just not seeing the whole picture. We're not seeing the whole U shape. But I did make it a little bit rounder when I drew it in. And then we do the exact same thing for our last section, our 2x minus 6. And those need to be x is greater than 2, so I'm going to do 3, 4, and 5. So that'll be 6 minus 6, which is 0, 8 minus 6, which is 2, 10 minus 6, which is 4. So when x is 3, we are at y is 0. 4, we are at 2. And 5, we are at 4. 1, 2, 3, 4. Is that right? That looks a little weird. Nope, that's right. One other thing that you should probably do, because here's what happens. Notice that from here at 2 to here at 3, it looks like we would just draw a straight line across. But we don't know if that's actually what happens. So even though we're not going to equal 2, we should compute what's happening at 2 so we know where it starts. That'll be 4 minus 6. So when 2 is going on, we're actually down at negative 2. We're going to do a jump like we did on our previous one, where we're going to have an open circle down here, and then we have this nice linear function for the rest of our piecewise. So use these values that they give you up here as kind of like your endpoints so you know what's going on at those. Just know if it says strictly greater than or strictly less than, you're going to have an open circle at that spot instead of a filled in circle. So this one's a little bit more complicated looking than our last one because it deals with 3 different functions instead of just 2. And again, on the My Math Lab, I believe all of these are multiple choice. They don't make you graph in all these little pieces. But you could be expected to graph these in on an actual test day because test days are pencil and paper. So it is good to know that. And you have to be able to graph them to some extent in order to pick up which one is correct when you are given multiple choice. Are there any questions on how we did these different piecewise graphs? Again, I very strongly recommend 2.5, looking ahead at that table of the basic mother functions so that you get a gist of what's going on in these functions. And if you Google it, like they have a whole bunch of other functions that are also classified as mother functions. I listed these 8 because these are the ones you're going to come in common or like in contact with the most in this class. There's even pictures or shirts. I need to get one of the shirts where it has like dancing people, like a dancing stick person, and these are the arms of the stick person so that you can see what's going on with those functions. So again, that's from 2.5, which we will cover in a couple of days.